So welcome everybody to our Gamma seminar. Today we have the pleasure to guest Mats Vermeeren. Sorry if I don't pronounce it properly. Thank you, Mats, for accepting our invitation to give a talk. He will talk about contact variational integrators. So Mats, the floor is yours. Thank you for accepting our invitation.
Oh, thank you for having me, and thank you for the suggestion to revisit some of this work from a few years ago. So most of what I will be saying is, in a sense, an updated version of our joint work with Alessandro Bravetti and Marcello Seri, back at the time when I was still in Berlin. So I've also credited the research center I was part of at the time, discretization in geometry and dynamics. And this idea of variational integrators, whether it's traditional or contact, really fits with the spirit of that center, where the slogan was, you discretize the theory, not just the equations. And in our pre-discussion, I already mentioned that the start of this story for me personally was the Ibero-American meeting in 2018, where I met Alessandro, who gave a poster on contact mechanics, and we started talking and spotted this opportunity to look at the discrete sides. And then our main paper is this one here, so also with Marcello Seri from Groningen. And then a few years later, a lot of this was reformulated in a nicer geometric language in the second paper on the slides. So I'll try to do a bit of both pictures, how we originally saw it, and point out that the more geometric versions were appropriate. So this is the plan. I'll say a little bit about the Hamiltonian picture as well, but my focus will be on the Lagrangian side, so on Herglotz variational principle. I'm not sure if this audience needs a lot of background on symplectic dynamics, probably not. But
don't worry much about that. The basics are well known.
yeah. So yeah, I will skip through this. What maybe I should spend a little bit more time on is the idea of geometric discretization, which is, in a sense, part of numerical mathematics, but the philosophy is very much geometric in the sense that your discretization is not motivated by minimizing some kind of local error, but it's motivated by preserving the geometry that was on the continuous side. And it turns out that in many cases, this serves the same purpose and also leads to discretizations that are numerically performing very well. So I again don't need to go through the detail. A map is called symplectic if it presents the symplectic form, etc., etc. And for the purposes of our talk, variational integrators, the idea is that instead of finding a continuous curve that minimizes the action integral over time of the Lagrangian, we now have an action sum, so a finite sum of contributions like this. And where the idea is that our discrete Lagrangian, my discrete Lagrangian will always be upright, capital L, my continuous Lagrangian will be a calligraphic format. And you could say the discrete Lagrangian approximates the continuous one. It's better to think of it as the discrete Lagrangian approximates what is sometimes called the exact discrete Lagrangian. So the action over one time step, the step size is given by h here. So the minimal possible value of that is the exact discrete Lagrangian, and you want your actual discrete Lagrangian to be an approximation to that, because you don't usually have the exact discrete Lagrangian, because if you have that, you have exactly solved your problem. And to leading order, it's the same thing to say that L approximates the exact discrete Lagrangian, or L approximates the continuous Lagrangian. A lot of this story, again, I think you know the basic properties of these things. A lot of the story, especially from the variational integrator perspectives, is in this review paper by Marsden and West. The next part still probably counts as introduction, and I assume it's known to most people here. What is contact geometry? Well, it is an odd dimensional analog to symplectic geometry. And in the most geometric sense, a contact structure is a distribution of hyperplanes in subsets of the tangent space of this odd dimensional manifold that is maximally non-integrable, meaning that it's impossible to have a submanifold of high dimension that is tangent to this distribution. And the most non-integrable you can get is that if this tangent submanifold is at most of dimension n, where 2n plus 1 is the total dimension. Most of the time, we'll not be working explicitly with this distribution of hyperplanes, but rather with one form, because we can think of a distribution of hyperplanes as the kernel of a one form. And then this integrability or non-integrability condition amounts to this expression. If we take the exterior derivative of the one form, take the nth power, and then wedge it once more with the one form itself, it should not vanish. And there is one distinguished vector field in a contact manifold, which is called the Reeb vector field. It's characterized by the properties that if you plug it into the contact form, it gives you a constant 1. And if you plug it into the exterior derivative of the contact form, you always get 0. And since the geometry is really about the hyperplanes and not the one form, we say that some function is a contact transformation if it preserves the one form up to a scaling. Because if we multiply the one form by something scalar, it still has the same kernel, so it still describes the same distribution. And similarly, for the infinitesimal criterion, we say that X is a contact vector field if the Lie derivative along X of the one form is a multiple of the one form. So it's just, well, maybe the G should be different, but it's the infinitesimal version of that scaling. I often prefer to work in coordinates at first. And just like the symplectic form has Darboux coordinates, the same is true for a contact structure. And it looks very similar, but we're now in odd dimensions, in dimension 2n plus 1. So the canonical coordinates would be nx coordinates and p coordinates and one additional coordinate that I denote by z. And then the one form is dz minus p dx, where whenever I write something like p dx, I really mean the sum of pi dxi. And in these coordinates, the distinguished vector field is just d dz. So maybe this is notation I should have introduced. D subset is just d dz for me. And in addition to this one distinguished vector field, we can construct Hamiltonian vector fields. So for each scalar function on our manifold, which we call H, the Hamiltonian, we can associate a vector field to it by these two properties. So we want it by definition to be a contact vector field. So the Lie derivative of the one form is proportional to the one form. That's not enough to have a unique definition of X. So we need the second part of the derivative of this definition as well to characterize the Hamiltonian vector field uniquely, which is that if we plug it into not the symplectic, the contact one form, we get up to sign the Hamiltonian.
Sorry, one question, because why you drop the 0 in the function gh?
So if you require these properties just with the fact that there exists some function gh, that's then sufficient to compute that gh must be given by this one here. So the wave vector field applied to the Hamiltonian with a minus sign. So it would be completely equivalent to put this expression into the definition. But my opinion is that if you can get away with a weaker statement saying that there exists some function and obtain an equivalent definition, it seems like the more natural definition to at first define it with an arbitrary function and then deduce that it must be given by this one here.
Okay, curious.
I have another remark. In the previous slide, you defined, I forgot how you call it, like contact or infinitesimal, well, what you call contact vector fields are precisely contact Hamiltonian vector fields. You can prove that it's an if and only if condition.
Yes, exactly. Just like in the symplectic case, some vector field preserving the symplectic form is Hamiltonian. Yeah, so thanks for that remark. And if you work in the canonical coordinates, the equations of motion you get are here. So the Hamiltonian vector field in coordinates is defined by these expressions, where you can see that you can consider it as a perturbation of the usual symplectic equations in P and Q by this additional term and then an additional equation in Z. Similarly, if you plug it into the definition, but try and formulate it not on the level of eta, but on the level of its exterior derivative, then you get something that looks like the definition of a symplectic Hamiltonian vector field plus a perturbation. And one of the main applications of contact mechanical or contact Hamiltonian systems are mechanical systems with linear dissipation. So the energy or the Hamiltonian is not conserved for contact Hamiltonian systems. It involves according to this equation, or if you prefer it in the abstract, according to this expression with the wave vector field and the Hamiltonian. And in practice, when you take a traditional mechanical Hamiltonian and add a scalar multiple of Z, then you get the mechanical system where there is a damping term with this same coefficient becoming the friction coefficient. So that's one application of symplectic Hamiltonian systems. There are other areas where it's relevant, and I think these references are a bit outdated. There are more recent papers on these topics. But for the talk today, it makes sense just to keep the mechanical example in mind. Right, so if we want to do geometric integration of Hamiltonian systems, whether that's on the symplectic or the compact side, there are a couple of different ways you can go about it. The two that I will mention are obviously the variational integrators from the title, but also the splitting integrators. So if you have a Hamiltonian that is separable, so in the symplectic case, that would just be kinetic term not involving positions plus a potential term not involving velocities. In the contact case, I impose that the P, X, and Z dependence all decompose. You can consider the Hamiltonian as a sum of these three parts. So the Hamiltonian vector field also becomes a sum of three vector fields corresponding to these three Hamiltonians. And the benefit of doing that is that each of these vector fields is explicitly integrable. Its flow can be exactly written in terms of these relatively simple formulas. So we can exactly follow each of these flows by a small step. And the idea of a splitting integrator is to compose a sequence of such steps such that the combination of, in this case, these 5 steps is a reasonable approximation to the actual flow of the Hamiltonian vector field of the whole H over the same time step H.
Sorry, Mats. One question, because as you said, there are many examples of this type, but do you know any more general examples, in particular those related to the Z variable, that it will not be only linear, because it's something that it always happens. Well, it frequently happens. Do you know something more general with applications that can be interesting, and it cannot be reduced to this case?
No, so I mean, it's easy to write down a Hamiltonian that is of a more complicated form in the Z dependence, but I don't know any concrete example that has a clear application.
And do you have any guess about why it's like that?
No, and my guess would be that it's more about my own ignorance than the limitations of the theory.
I'm sorry, my guess will be that this is just because it is not physical. Because in all those cases, when you have T star M times R and you have a contact structure on this, it works because you can, I mean, you can switch, in all those physical examples, you can just switch off this dissipation, yeah? For example, I don't know, put the friction coefficient to 0. No, it is not friction, it's viscosity rather. So put viscosity coefficient to 0 and then everything works. But you have to be able to, you have to have this separation between phase space and this additional parameter to be able to do that. And then if you want to have that, and this is the physical thing, the physical condition, then you end up with exactly this example. But of course, I mean, one can write even, we did this, we wrote some examples on the Mobius band, on the first jet space of the Mobius band, which is it is non-trivial, non-orientable. There is no general eta, but of course, and everything works beautifully. However, it is an artificial example.
I don't know, Xavi, maybe I think that you told me, if I remember, that you had another example where this appears. But because saying that artificial is sometimes too much, because it could be some kind of certain cases.
No, okay, this one on the Mobius band
Yeah,
was completely
I meant,
artificial.
okay,
Yeah.
yes, the Mobius for sure. Well,
And
I mean, it's quite
I've
weak.
got one equation. I've got one equation from Xavier. It was about parachute equation, and it
Indeed,
had
this
a
is
different.
example.
It had a different dependence on Z.
Yeah, I mean, there was something of this sort, because I remember I wasn't sure about the parachute. I thought it, but I remember that Xavi for sure knows, because it's a typical stuff. And what you said, Cassie, about switching off the dissipation is, well, I think that it's something of that, something like that happens, yeah. So thank you. Maybe you can continue, Mats. But
Yeah, well,
we
just to
wanted to
conclude
discuss.
with this, there's also this paper of your collaborator Bravetti. I forgot which were the other co-authors of scaling symmetries, where they reduce certain symplectic systems quotienting by a scaling symmetry. Sometimes it's possible to reduce them to, and there they have some examples that seem to have physical motivation, like some cosmological models and so on.
Okay, yeah, I should have another look at that then. Thanks.
Please.
Right, so this is one way to get a geometric integrator for contact systems, at least those in the, let's say, physical form. And the one I wrote down here is of second order, which is obtained by making it at least of first order and then symmetric. But you can get it to any order by a trick that is borrowed directly from the symplectic setting, where it was introduced by Yoshida. And there is an explicit formula if you have an integrator of some order 2n, then you can compose 3 steps of it to get an integrator of order 2n plus 2. So with this splitting approach, you can get contact Hamiltonian operators for the separal Hamiltonians to any order you would like. But that's not what we did in that first paper, and that's not really what I want to talk about today mainly. The other approach is that of variational integrators. So in the symplectic case, if you discretize the Lagrangian and minimize the corresponding discrete action, you automatically get a symplectic integrator. And the same story translates to the contact case, where first we need to say, what is the variational principle? And a hint for this, if you haven't seen this before, is if you look at the contact Hamiltonian equations, the equation for Z is this one, where the right-hand side looks like the Legendre transform. So it looks like this should be L on the right-hand side. And that's exactly how the variational principle in this context works. We have, in a sense, an action-dependent Lagrangian, because the new coordinate Z keeps track of the action over time. So to put it differently, the derivative of Z is the Lagrangian, so the action Z at a certain final time would be the integral of the Lagrangian. And if the Lagrangian does not depend on Z, that's the familiar story and reduces to the symplectic case. But of course, the cases we're interested in, where we actually have contact dynamics, we have a dependence on Z in the Lagrangian. So if we wrote it down as an integral instead of a differential equation, it would be self-referential. So the variational principle, to put it a bit more precise, is that for any curve X into our contact manifold, or I'm being slightly inconsistent in the notation here. So TQ cross R here is the contact manifold. So in a sense, Q is just the configuration space, just the space of X's, not P's. So given a curve into configuration space, we define the Z part of our contact coordinates by some fixed initial value at time 0, and this differential equation Z dot equals to Lagrangian. And then we require that for variations of this curve X that leave the boundary points, so X at 0 and X at capital T invariant, the final value of this Z should also be invariant. So the action we're minimizing is Z evaluated at the final time. And this was originally introduced in some very hard to find lecture notes in German by Gustav Herglotz. And the sense I got from those is that he just did contact mechanics because he saw it as a way to generalize the usual calculus of variations, and must have thought, if you can do it more general, why not? So he seemed to just give his course on the calculus of variations entirely in this framework of action-dependent Lagrangians. There are a couple of ways you can extract Euler-Lagrange equations from this principle. The first one, which I think of it as a fairly direct approach, though the computations are not very nice, but I've seen it referred by Xavi and others as the implicit approach, is, well, we have this defining equation for Z, and we need to know how perturbations, how variations propagate over time. So we need to turn this equation for Z into an equation for Z dot, which just goes by the chain rule. And then for the sake of keeping notation manageable, I group these terms and call them A. Those are the terms that don't depend on Z. And then I have something times dz. And the something, I could call it B, but it turns out the formula will end up nicer if I call its integral B. So this dl dz becomes the time derivative of B. And so we get an equation of this form, and it has a general solution in this explicit form, explicit but not very pretty. For our definition of A, that becomes this line. So we have an expression kind of like the intermediate step in the usual calculus of variation, where we have a delta x and a delta x dot. So we want to integrate by parts so that we only have delta x. But because this whole thing here is multiplied by this exponential of minus b, the integration by parts gives us two terms on the next line instead of one. The first term is the usual one, where the time derivative goes on to the momentum term. But then there's also a term where the time derivative goes on to the exponential here, and that gives the final term in pink here. So if we restrict, as I said earlier, to variations of x that vanish at the boundary, then dx at time t and dx at time 0 will be 0, and we fixed z at the initial time, so this also will vanish. So all boundary terms vanish, just like in the usual calculus of variations, and we are left with the pink bit as the generalized Euler-Lagrange equation. So the top of the slide is what I just said, and the generalized Euler-Lagrange equation, or the Herglotz equation, is the first two terms agree with the usual Euler-Lagrange equation, and then we have a term that involves the z derivative and the momentum associated to the Lagrangian. And just like in the symplectic case, you can use the boundary terms of the calculation we just did, and that I said were all 0, but we can still use the boundary terms to recover the contact structure that is being preserved. And to do this, just like you would in the symplectic case, you now only think of solutions to the generalized Euler-Lagrange equations, but you allow the endpoints to be varied. So only looking at solutions means the integral term is now 0, but now the boundary terms are not 0. And if we group the boundary terms, we get two things that look very much like our contact form. If we think of dl dx as the momentum p, then the terms I've grouped here are p dx plus dz. So that's our expression in Darboux coordinates of the contact form. And the first two terms can be grouped in the same way. So you get that, well, as we should have expected, the flow produced by this variational principle does not preserve the one form exactly, but it changes it by a scalar factor, which is given by this exponential of b. But that's exactly the right definition for a contact map. And so this verifies that the variational principle of Herglotz actually produces contact maps. Another way to get to the equations is to impose our differential equation for z as a constraint. So the action, really the action we want is z at the final time. But if we want to impose the constraint by Lagrange multiplier, then it amounts to adding this integral term. And if we're writing the integral anyway, it's slightly more convenient to write zt as z of 0 plus the integral of z dot. And z of 0 is kept constant. If you want, you can put it to 0. So really, the action now is of an integral form. Obviously, since we're dealing with a Lagrange multiplier here, if we vary lambda, we just get our constraint equation back. So nothing surprising there. And if we vary x and z, so now we are also varying z, because we're not explicitly using this equation to determine z, we've put it in as a constraint. So we vary both x and z now, and we get these two equations. The second one, you can, for example, solve for lambda dot, and then plug into the first one, and then the first equation becomes this one. If you divide by lambda, you recover exactly the same equation as on the previous slide. So this is a different way to get the Herglotz version of the Euler-Lagrange equation. And from the first part, you can see that lambda will be kind of like an exponential function. If the LDZ is constant, it will be an exponential function. So in that case, in particular, lambda will be never 0, so it's fine to divide by it. But also, we can play the same game with varying the endpoints to get the contact structure. In this case, if we keep to solution curves only, but vary the endpoints, we again get two terms involving the contact form in their book coordinates, and now the scaling is given by our multiplier lambda. The strange thing about this that I don't quite understand is that in generalizations to field theory, these two approaches may not be equivalent, but in mechanics, they yield exactly the same. Something I haven't mentioned yet is the analog of Noether's theorem in the contact setting. If you have a symmetry in the symplectic setting, you get a conserved quantity. In the contact setting, you get a dissipated quantity. And again, you can get this out of working with the boundary terms of the calculus of variations. So if something, let's say our vector field V is a variational symmetry, it means that if we take variations of the action in the direction of V, we get 0, even if we're not looking at solutions. So again, playing that game with the boundary terms of the calculus of variations, you find that this expression, which is lambda times the contact one form evaluated on the symmetry, is a constant. So the bit without the lambda, if we just take the one form evaluated on the symmetry, it has to be proportional to 1 over lambda. And since lambda typically is something exponential, this becomes a dissipated quantity. And it's important to note here that lambda does not depend on which symmetry V we put in here. So if we have several symmetries, we have several quantities that are dissipated at exactly the same rate, so their ratios would still be constant. And in particular, if you're working in coordinates, the time derivative as your variational symmetry, or if you're working more abstractly, just put in the Hamiltonian vector field, you find that the dissipated quantity is the Hamiltonian itself. Or in this setting, rather, the Legendre transformation of the Lagrange. So how much of this can we recover in the discrete setting if we want to use this theory to come up with numerical integrators? Pretty much everything, but there are some choices to be made how you present the discrete story. So again, the idea will be to approximate your continuous Lagrangian, or more precisely, the exact discrete Lagrangian, which is the minimizer of the action over one time step, by now a discrete Lagrangian. And at first, I'm writing it down here as we presented it in our paper, which has some advantages, but probably is not the most natural way of doing it. I allow the discrete Lagrangian to depend on two neighboring points for x and also two neighboring points of z. For x, this is natural because you need to be able to approximate its time derivative. For z, the only dependence on z was z itself, so it's maybe a bit unnatural to put both points zj and zj plus 1 in there. One benefit is that you can, in a very explicit way, write down symmetric discretizations. And the Herglotz variational principle in the discrete setting is what you would expect it to be. So we change the differential equation for z into a difference equation. So the increment in z is step size times the discrete Lagrangian. And then if we're working from, well, a time 0 to time n, step 0 to step n, then we look for the discrete curves such that, so the sequences of x's such that the induced value of zn does not depend on any of the values xj in the middle of our curve. So like the continuous case, we will keep x0 and xn fixed when we take variations, boundary points are fixed, but differentiating with respect to any other x in the discrete curve should not change zn. And I mean, if you're looking at equation star here, you can, unless it's really degenerate, you can solve for zj plus 1 and get an explicit recursion for z with a Lagrangian that only involves one of the 2 points in z. So this is probably the more natural way of phrasing it, to have a Lagrangian only depending on one z. And that's also the form of Lagrangian I'll use going forward, but in some of the results I'll point out how they would look if you allow Lagrangian to depend on 2 steps of z. So how do we get discrete order Lagrange equations out of this principle? We can use the same 2 approaches essentially as before. We can start from the difference equation and turn it into a difference equation for how delta z would evolve. Except in the discrete case, delta z can always just be composed into a finite number of partial derivatives. So it's efficient to, rather than take this formal delta operator, to just take partial derivatives of this equation with respect to the variable xi, where I is any step along the curve. And so if we do this, then by chain rule, you get this massive expression. So my d1, d2, d3 are partial derivatives with respect to entry 1, entry 2, and entry 3. And well, I get these slightly weird partial derivatives here. And the x's are effectively my independent variables. So these partial derivatives will be 0 unless I and j happen to coincide, or in the first case, I and j minus 1 will happen to coincide. So if I and j are well away from each other, then the only contribution here is the first term. And in particular, if the step size is small enough, then the term or the factor in brackets here, will not be 0. So I've missed some indices or misprinted some indices here. So this one should be the D1 and this one should be the D3. And then this should be the Z. Sorry about that. The point I was trying to make is that if this factor here, if h is sufficiently small, this factor is not 0. So one of these z derivatives is 0 if and only if the other one is 0, if I and j are not close to each other. So actually, our condition that the final value of z will be independent of all intermediate values turns out to be equivalent to just checking neighboring time steps. That if I vary xi, the next zi plus 1 will not change. So all we need to check discrete Herglotz principle is this partial derivative. But to compute that partial derivative, we need one more, which is if we differentiate zi with respect to xi, zi is given by this differential equation, so the only involvement of xi will be here in the second entry of the Lagrangian. So zi with respect to xi is just one partial derivative of x. To get to the partial derivative, we actually need to check. We take the next iteration of the difference equation. There are a few more things that could depend on xi. So zi itself will depend on xi. Then we have xi explicitly in the Lagrangian. And then again, through the zi in the Lagrangian, there's also an xi dependence. So we get these three terms, plug in the value of dzi dxi, we compute it, and then we get an expression that only involves partial derivatives of the Lagrangian. And by the argument on the previous slides, this partial derivative being 0 is equivalent to Herglotz's principle. So we get this expression as the discrete Herglotz or Lagrange equation. And if you ignore the final term here, just look at this bit. If you've seen the symplectic side of the story, this is exactly the Euler-Lagrange equation you get in that setting of a discrete Lagrangian in the symplectic context. If we allowed L also to depend on the next set, you get something that is slightly more complicated. Now there's a D4 in the picture as well, but again, the leading term is that of the usual Euler-Lagrange expression. And we can have a look at how these relate to the continuous case. I'm doing this here for the case where there can be a D4, but if you only allow one Z entry, then all of the D4s can be set to 0. So the first two terms, as I said, they're the usual discrete Euler-Lagrange equations. So if you have a consistent discretization, if your L is a reasonable choice, then this will approximate your usual Euler-Lagrange equation in the symplectic sense. And then for this prefactor here of the additional term, in leading order, it's proportional to h times d2 of L, which can be understood as a discrete momentum, and it will approximate the continuous momentum. And then the discrete derivatives, d3 or d4, those are derivatives with respect to z, so they should approximate the z derivative of the continuous L. So if your discrete L is a consistent discretization in a suitable sense of the continuous one, you also get that the discrete Euler-Lagrange equation is a consistent discretization of the continuous Euler-Lagrange equation in the sense of these approximations. And this is the one point where I think the formulas are much nicer if you include the double z dependence. So if you include the d4 derivative, then you can rewrite this expression in this quite symmetric form. And both of these terms approximate the continuous momentum. So you get, in this version of the discrete Euler-Lagrange equation, you get an expression that is momentum matching. Like in the symplectic case, you can write the two parts of your discrete Euler-Lagrange equation as being two different expressions for the momentum, and the solutions are those for which the momentum match. You can give the same interpretation to this discrete Herglotz equation. And that then immediately in these coordinates where the p is given by the momentum gives you your Darboux coordinates for the contact structure. The other approach we had, in this talk, we didn't have it when we wrote the paper in 2018. The other approach is that of the Vaconomic setting, enforcing the constraints by a multiplier. So like before, we can think of the action as the initial value of z plus previously it was the integral, now it's the sum of the increment in z plus lambda times the constraint. The constraint for us is the difference equation. Analogous to the continuous case, we now vary both x's and z. We get two equations. We can solve one of them for, say, lambda I minus 1, and then plug that in the other one. So you get, in the end, an equation where lambda I minus 1 doesn't occur anymore. You only have lambda I. And furthermore, it's linear in lambda I, so we can divide it away. And the remaining expression is, again, the discrete version of Herglotz equation. So we recognize the derivatives with respect to xi, which are the usual discrete Euler-Lagrange equation, and then this additional term that is can be read as a momentum times the z derivative. So it's quite nice to see that in the discrete case, you have the same options of how to compute the discrete Herglotz equation. And you can also turn this around. Every contact map has a Lagrangian in the Herglotz sense, which is again perfectly analogous to the symplectic case, both in terms of the statements and how you prove it, because like in the symplectic case, there is a notion for contact transformation of a generating function, and that generating function is exactly what our discrete Lagrangian is. So every contact transformation has a generating function, and this generating function fits perfectly as the Lagrangian in the Herglotz principle. Now, part of the reason why geometric integration is useful, and in particular symplectic integration is useful, is that if you use a difference equation obtained that way, it will remain very close to a continuous system of the same structure. And this is how, on the symplectic side, you show that the energy behavior over long times is very good. And more explicitly, how this works is through backward error analysis. So you don't try to look for how big is the error I've made by discretizing my continuous system, but you look for the inverse question saying, what continuous system would I have solved perfectly with the discretization I chose? So out of my Herglotz principle, I can decompose the equations as the Euler-Lagrange equation, which I can suggestively write as the second order difference equation. And the first equation here is just rewriting the difference equation for z that defines the Herglotz principle. So solutions, I look at solutions of this difference equation, and I ask the question, what continuous system would they have solved exactly? So instead of thinking of this as a difference equation, I think of z and x as continuous functions, and I said, well, if zj is z at t, then zj plus 1 should be z at t plus h. And similarly for x, where xj minus 1 would be at x at t minus h. And then Taylor expand everything you can get your hands on. And then formally, you get a set of differential equations for z and x that involve a power series in the step size. And usually this power series is horrible, doesn't even converge, but still by truncating it, you get error estimates. And the point why symplectic or contact doesn't matter, why variational integrators work nicely or symplectic integrators work nicely, is that the modified equations you get in this sense are again Lagrangian equations. So in our setting, if I use the modified Lagrangian, so this power series I get on the right-hand side, if I use that as my continuous Lagrangian in Herglotz's principle, then my second equation that interpolates my difference equation for x will be exactly the Herglotz or Lagrange equation coming from this Lagrangian. So the continuous system that only exists in a formal sense, but in that sense interpolates the solutions of the discrete system, it is again a Herglotz Lagrangian system, so it is again a contact system. Now, in the symplectic setting, from this you say that, well, if my discrete system is interpolated by a continuous Hamiltonian system, I know it preserves the energy of this continuous Hamiltonian system, and that's where you get the long-time behavior of symplectic integrators. Here you could do the same. You can do the same and say, well, my discrete variational integrator is interpolated by a continuous contact system, so it has a dissipated energy and maybe other dissipated quantities. And so you can make the same long-term energy conservation argument that the integrator will stay close to the energy of the actual system. But the use of this is not as clear as in the symplectic case, because the energy dissipates away. And if the energy goes to zero in medium to long time, then what information do we actually get out of the fact that we have long time good energy behavior over a very long time if the energy goes to zero or anyway? And I think this is reflected in the simple numerical experiments we did at the time. So there wasn't a very strong experimental case for contact variational integrators. If we look at, say, simplest possible system, harmonic oscillator with some damping, very small damping in this case, then the contact variational integrator of second order we constructed was very similar in performance to just using the leapfrog integrator, which is a symplectic method, which doesn't really fit here, but the numerics weren't that bad. And if we used slightly bigger damping, then the contact integrator did come out with the lowest error. So there's definitely some evidence that it makes sense. But as I said, since the theorems we could potentially get about long-term behavior talk about a range of time after which the system gets damped to equilibrium anyway, it's unclear what the practical relevance of such long-time error behavior theorems would be. So that's still for me a bit of an unclear question. It's a very satisfying theory, just like that of symplectic integrators, but what the actual practical implications are, are not entirely clear to me. So we also looked at some time-dependent examples. I think geometrically they're, strictly speaking, represented by co-compact systems, but on the level of equations or in coordinates, you can just plug in a time dependence and copy everything over and it will make sense. So one particular system we looked at in a follow-up paper relates to orbital mechanics, where you have a flexible satellite, and because it's flexible, the torque that gravity exerts on it will actually introduce a dissipative term. So the simulation done here is that initially the satellite is in a fixed orbit, and this is where the time dependence in our system comes in, because we just impose that this orbit is fixed, and that's the time dependence. And then we let the rotation of the system freely evolve. At first, the satellite is rotating very quickly, but this gravitational torque on its flexible body introduces dissipation. So eventually it stops spinning around and goes over into an oscillating behavior, and then very slowly stops spinning and just converges to an equilibrium where one side faces the planet. So in a sense, time-dependent systems might be a situation where you have more use for long-time conservation results, because maybe with the time dependence you don't reach equilibrium. But in these examples that we studied, we do, in maybe the sense of a reduction, we do get to an equilibrium where the dissipative term goes to zero. So again, in the long time limit, you don't actually see the contact structure anymore. So yeah, that's for me still on the more applied side, a big open question. It's a beautiful discrete version of a beautiful continuous theory, but whether it's useful, hopefully so, but probably not as much as symplectic integrators have been useful in practice. Right, so that covers the first point of my conclusion. Herglotz principle is often referred to as an action-dependent Lagrangian, which I've mentioned, because this z variable keeps track of the action of your system, but it is also in your Lagrangian. And essentially, once you have Herglotz's principle, then all the discretization we do just transfers the exact same IDs from symplectic integrators or variational integrators for symplectic systems, transfers all of those IDs over to the contact sites, and everything works in essentially the same way. Right, and so I put our two references on here, and the more geometric version, and I'm not exactly sure where the vaconomic principle was first used for Herglotz, and there's a third way of doing things as well. And I've put this final paper on here. I don't think it has anything discrete in there, but it gives a very nice introduction to the different ways you can treat Herglotz's principle to get equations of motion out. Right, and on that note, I'll finish up. So thank you very much for your attention.
Thank you very much for your nice talk. So, is there any question, remark, comment?
I have a question.
Yes?
I know almost nothing about contact integrators. I know some things, but also my knowledge is limited about symplectic integrators. But at some point I stumbled on this idea of, so this is a kind of mixing symplectic integrator with variational approach, which is the following. You mentioned at some point that, of course, if we have the solutions of the equations we want to solve, we can write this exact discrete.
Exact discrete Lagrangian, yes.
Exact discrete Lagrangian. Okay, so there was the idea that No, because if you have an action integrated along the solution of Euler-Lagrange equation, this is a generating function. This is then called two-point Hamiltonian function or something like that, and it generates a relation between initial conditions and a symplectic relation between initial conditions and the point after a specific time. Yeah.
Yes.
So the idea was to just take this formula, and since you don't have the solution, then you can integrate this true Lagrangian, which is in the action, in the definition of the action, you integrate it on something which is not the solution, but something, maybe a piece of straight line, yeah. And then,
Yes.
yeah, so and then you necessarily get a symplectic integrator, because what you get is a generating function. The problem is that if you take a system which is more complicated, that I don't know, than a harmonic oscillator, then this thing, the relation you get is implicit. And if you really need an integrator, you have to somehow solve an implicit equation, which may be complicated. However, in many cases, it is possible. You can do it. So
Yeah.
is there anything like that for the contact system?
So I think, again, it depends on whether your Lagrangian separates. So if your Lagrangian separates in a kinetic plus potential plus z part in the contact case, then a lot of the ways of approximating this exact discrete Lagrangian will actually lead to explicit equations. If your Lagrangian doesn't separate, then I think both on the symplectic and the contact case, it's very unlikely that you'll get an explicit integrator out of it.
Yeah. Now, for non-separable Hamiltonian, there is this trick of doubling the space. I don't remember at this moment what was the names of the guys who invented it. You can take two copies of your system, then switch momenta from one copy to the other, and then it becomes separated, but you have to add some harmonic-like term to keep this together. However, I mean, and this is very effective. I mean, this is theoretically nice and quite effective. However, you end up with a phase space which is twice as big. So
Okay.
yeah, in terms
I'm not
of
familiar with this.
Kasia, was it Bateman, maybe?
no.
So I think
No. I know about this because I've read a bachelor thesis of somebody who just used it, but I don't remember the names of people who invented this trick.
so. Bateman did something similar to get a Lagrangian description of dissipative systems without using contact geometry by doubling the phase space.
Exactly. For instance, in the heat equation and things like that.
So I will try to
Go ahead.
find this
I
thing.
don't know the original author, but this trick, I remember it was also used in the PhD thesis of Rodrigo Sato, who was a student of David Martín de Diego, and did some discretizations of four systems, I think.
Yeah, I will know those names in a moment because I'm just looking at the literature in this thesis that I read, and definitely there will be I think the name was Tao. 2016, explicit symplectic approximation for non-separable Hamiltonians. Physical Review E, and the name is Tao.
Okay, I'll have a look at that.
So this can be, for example, used in the contact, because you can take a symplectization of the contact structure. Then again, you enlarge your space by one dimension, yeah. And then if you have a non-separable system, you can multiply it again, and you can solve numerically non-separable case. However, I mean, there are many variables. So if it is numerically effective, it probably depends on the case.
Okay, so apart from a comment by Asher that wrote about the translation of the Herglotz lectures in German, that it's on the chat, you can find it.
Okay. Didn't know
I
they were
realized
translated.
when I was preparing my thesis, because in most of these papers they cite the original paper in German, which, as you said, is very difficult to find. I guess it's just in a physical copy in some library in Germany. But
Yeah,
turns out
so
it was
I
actually translated. So.
Yeah, I have a scanned copy because when I was still in Berlin, I went through interlibrary loan. I got a copy, and then I thought, okay, this was so hard to get. I'm going to just scan it all.
So at this point, I can advertise the library of the Mathematical Institute of the Polish Academy of Sciences. They have this book.
Oh, good.
In general, they are very good, and many times people, well, lately not much, but previously they asked me for copies of weird papers that were almost lost, and they frequently have a copy of everything. So they are quite good indeed. Anyhow, we are running out of time. Maybe we'll run. Any other question or remark? Short? No. Well, thank you very much, Mats, for your nice talk. It was a pleasure to have you. Please send us your slides, and I will send you a couple of questions one day because, well, we have no time. So I'd love to everyone about what you did. It would be nice to know your opinions. So thank you very much, everyone, and we see you in a week. That we have, wait a second, Joanna Gonera, I think that it was, yeah, from the University of Łódź. Okay, we will see you next week. Thank you very much.
Bye. Thank you.
See you.